Welcome everybody to the third lecture of microwave engineering, second lecture on transmission line, and today we're going to be talking about Smith chart. So the Smith chart is a graphical aid for solving transmission line problems. So the formulations that we covered in the previous lecture, in lecture number 1, is the analytical solution, but there is like some sort of like an aiding chart that's frequently used for solving microwave problems, and it has the advantage of like visualization. You can sort of like see the problem and feel it more than the equations. The equations is very important, the equations is more accurate, but to visualize the problem, Smith chart does have this advantage. So Smith chart is not the only chart available in the scientific community for solving microwave problems, but it is the most famous one. Also, Smith chart is not a new thing. It's an old tool that's starting 1939, and it is part of many CAD softwares. You can it's very popular to see it in the analysis in many simulation packages. And Smith chart is based on polar plot of the voltage reflection coefficient gamma, as we're going to see. So this is the Smith chart. It looks like a messy chart, but when you use to it, you will find it's very useful. We're gonna come to the details of different parts of Smith chart shortly. Okay, so how would we draw this Smith chart? As I said, Smith chart is a polar representation for the reflection coefficient, voltage reflection coefficient. So if we write the voltage reflection coefficient in the polar format, it would have a magnitude and phase. This is the reflection coefficient at the load, and we does have developed analytical expression for the reflection coefficient. So on Smith chart, the magnitude of the reflection coefficient, which is always less than or equal to 1, is plotted, as I said, in polar format. The angle would be anywhere from minus 180 to plus 180. The measurement of the angle is counterclockwise, starting from the right hand side of the horizontal diameter. We'll talk about this in more details. Also on a Smith chart, we are using normalized quantities. So for example, if we're talking about any Z, any impedance, we normalize it to the characteristic impedance of the transmission line, and we use lowercase for this. So if we have a lossless transmission line with a characteristic impedance Z0 that is terminated with a load impedance ZL, the reflection coefficient expressed in terms of the normalized load impedance, which is ZL divided by Z0, equals Z small l minus 1 divided by Z small l plus 1. So this is in general a complex quantity that's expressed as a magnitude and phase. Also, we can just work this out to express ZL as a function of the reflection coefficient, as we did before. The normalized impedance equal 1 plus reflection coefficient divided by 1 minus reflection coefficient. So if we write the reflection coefficient into Cartesian into two components, real component and imaginary component, same thing for ZL, the load impedance. Again, small letter means normalized, which will equal real component plus J multiplied by complex component. If we come back, now we substitute this real and imaginary into the expression or the relation between ZL and gamma. We'll have this expression, real part plus J imaginary part of the normalized impedance equal this expression in terms of real and imaginary part of the reflection coefficient. We just simplify the equation by having a real component in the denominator. We can now express the real component of the load impedance and the imaginary component of the normalized load impedance in terms of gamma I and gamma R, the real and imaginary expressions or components of the reflection coefficient. Solving those two equations together, we will have this expression. So this expression are real component minus constant plus imaginary component equal a constant, which is an equation for a circle, and this circle is shifted in the gamma R component. The second expression is very similar. It is an expression for a circle that is shifted in real and imaginary sides of the reflection coefficient. So again, back to the reflection, the Smith chart. The Smith chart, as I said, is a polar representation of the reflection coefficient, which means the reflection coefficient, like if we decompose this into real and imaginary part, the real part is expressed on the horizontal axis, the imaginary part is expressed on the vertical axis, and the magnitude of the reflection coefficient is a circle located with a center at the origin, and its angle, as we said, is measured from this side. So here from 0 to 180, here from minus 180 to 0, or you can say from 0 to 360. So this is the Smith chart, and as I said, this is the two equations that describe the relationship between the load impedance and the reflection coefficient. Both of them are expressed into real and imaginary component. So the first one, which is like the real shifted in the real, this is called the resistance circle. We're going to express or explain this more, and this expression is called the reactance circle. As I said, this is a circle shifted, so the radius equal this value, the radius square, and it is always with the center of this circle is on gamma I equal 0, which is on the horizontal axis, and it is shifted by this quantity. The other circle, which is the reactance circle, is shifted for gamma R equal 1, so it is on the gamma R equal 1 line, and the imaginary is also shifted, and the magnitude or the radius square of this circle does have this expression. So if we have R equal 1, RL means the load impedance normalized to the characteristic impedance equal 1, and we substitute here. So the circle has the center at R equal 0.5, gamma R equal 0.5, gamma I equal 0. The radius equal 0.5. So if we draw it, it will be like a circle with a center shifted 0.5, and it goes through the center of the Smith chart. We're going to see it shortly. And if we look into this expression, we'll find that all the resistance circles have the centers, as we said, on the horizontal axis, because imaginary part of gamma equals 0. All the circles pass through gamma equal 1 point, which we're going to show shortly on the Smith chart. So all the resistance circles does have their centers on the horizontal axis. All the resistance circles pass through this point. All of this is coming from the expression. So if real part equal 1, we said that the radius will equal half, and the center is somewhere here on the horizontal axis. So this is the circle of real part equal 1. This is the circle of real part equal 3. This is the circle of real part equal 0. So on and so forth. And this is what is shown on Smith chart. You will find here on Smith chart like the number. So this is 1. So this is the point or the index for the circle that does have a real component normalized of value 1, and then you find the other. So the further you go, it will be less, and the end, the largest circle, is the circle for real part of the load impedance equal 0. So 0.2, 0.3, 0.4, so on and so forth, 1, and then you go 1.2, 1.4, so on and so forth, and you go with the numbers, and this is the different location for constant real part of resistance. If we go for the reactance part, we'll find that the center is at R equal 1. R equal 1 is this point. So all the circles for reactance does have their their center on this line here. Gamma R equal 1. And the other point is related to the imaginary part of the load impedance. Also, we'll find that all the circles, they pass through the point of 1 and 0, which is this point. So all the circles for constant real part of normalized impedance, load impedance, pass through this point. All the circles for constant imaginary part of normalized load impedance pass through this circle here. And you will find that because the center for the reactance circle is on this line here, we'll find that, okay, so it is this circles here. So we don't draw the full circle, we just draw part of it. So those are arcs from the circles of constant reactance component of the load impedance. And because the reactance can be real and imaginary, the center for the reactance circles can be on the positive side or the negative side. So we have those curves here. So those are the arcs part of the circles of constant reactance for positive value and imaginary value. So positive and negative. So the imaginary part of impedance equal -1. So the center would be somewhere here and would have this part of this arc. If the imaginary part equals 0, we'll find that the radius equal infinity, which is very, very large circle. So what we see out of this circle is this line of imaginary impedance equals 0. So far, what we learned is that the Smith chart is a drawing for the reflection coefficient in terms of polar. So this is 0, the reflection coefficient would be like is represented by a magnitude and phase, or represented by a real and imaginary part. And this reflection coefficient is related to the normalized load impedance by those circles. So we have circles of constant resistance, which are those circles that does have their radius changing and their center always on the horizontal axis. The constant reactance circles are always does have the center on the axis, the line here, gamma equal 1, and they are changing. It can be like in the positive side and negative side, and we have those numbers drawn on the Smith chart. So here's the Smith chart, like does have a lot of explanation built in. We're gonna like study this more. So in a Smith chart, for example, everything is drawn to a scale. You can get a big, small, like Smith chart or a small Smith chart. In all cases, this radius, this length of the radius is corresponding to gamma equal 1. In the drawing, it can be like 6 centimeter, 8 centimeter, 10 centimeter, whatever. And it is all like, it can be scaled up and down and does have the same meaning. And you have a lot of scales that we're gonna show how to use on the Smith chart as well. So I'm just here like zooming in what is written on those sides, because on a Smith chart, we're gonna study that like motion towards the generator or motion towards the load, and also different scales that we're gonna point out shortly. So on a Smith chart, if we are representing a certain circle, this circle does have a certain reflection coefficient. Constant reflection coefficient corresponds to this red circle. Why? Because this is a circle of constant amplitude or certain amplitude. So this is gamma equal constant circle. And if we know the reflection coefficient, we know the relationship between reflection coefficient and standing wave ratio. Standing wave ratio is 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. So if we draw this, if we know this value of gamma, we can right away know the value of standing wave ratio. And all of these relations is shown here, and I'm gonna like show it shortly. Okay, so the reflection coefficient can be like anywhere on this circle depending on its value, like the magnitude and depending on its phase. And we're gonna go and see like more properties of the reflection coefficient. So we'll come back to those again. So the Smith chart, as we said, can also be used to express the load impedance. As well, it can be used to like solve graphically for the input impedance. So the expression for input impedance does have this value here. Load impedance does have this expression, and it's the same format as the input impedance. The only difference is that we have different angle here. So the angle is minus 2 beta L instead of theta. So load impedance does have this expression with theta. The like input impedance does have the same expression. If we talk about the normalized input impedance, it will have the same expression, but theta is replaced by e to the minus j beta L. And you need to notice that gamma here is the complex quantity, gamma here is the absolute quantity. So because of this similarity between the calculation of input impedance and load impedance, we can use a Smith chart to graphically find the input impedance. We know that the magnitude of the reflection coefficient on the transmission line, lossless transmission line, at any point on the line would be like of a constant magnitude. We just proved this. So the difference here, if we want to find Z input, what we can do is just come to the reflection coefficient and add like certain angle to it. So we just rotate on this circle of constant reflection coefficient by a value equal to beta L. Then the point that we're going to reach would be the reflection coefficient at the input of the circuit, and from it we can just read the input, normalize the input impedance of this circuit. So the Smith chart does have a scale around it. The property is calibrated, so you don't need to go with absolute. It just show from different point, like on the outer ring, different value for how much rotation that we had, and this rotation is like annotated in terms of length. We know that the impedance is periodical with a periodicity of like 0.5 lambda. So one full circle on Smith chart is corresponding to 0.5 lambda. So if we go for the scales here, you will find that it is like from 0 to 0.5. So one full cycle, and if we're moving in the positive L or negative L, it makes a difference. So one side is that we are moving from load towards the generator, which is we are moving away from the load, or the other side we are moving towards the load from certain point to the load. The direction of rotation will make a difference. So it is here you can rotate by certain degrees, or you can rotate by certain lengths, because the relationship is the angle is corresponding to 2 beta L. So you can rotate in either side. So this is in terms of the radial scales or the radial motion. Also, like because the impedance, the input impedance is like, again, as I said, it's like periodic by 0.5 lambda. So if you are starting at any point and you rotate for like 0.5 lambda, you will come back to the same point. So in this motion, the input impedance can be can be maximum, or it can be minimum. So it's changing as you move along the line. You can prove this from the expressions. One moment here, I need to correct this. So as I said, we can start like at any point on the circle for input impedance, and if we rotated or like moved for 0.5 lambda, we'll come back to the same point. In this rotation, we'll come to a point where the impedance is maximum and a point where the impedance is minimum. So this right horizontal axis is the location for maximum impedance, which is corresponding to maximum volt and minimum current. And the left side of the horizontal axis is the location for minimum impedance, which is the minimum voltage and maximum current. Also, if we look here, we'll find that standing wave ratio, as I said, like we can convert from like circle of constant reflection coefficient to a circle of constant standing wave ratio. Also, the reflection coefficient of current or voltage is this one here. This is the scale for it. Don't confuse it with this one, the reflection coefficient for power. It's two different things. We are working on the reflection coefficient for electric field or the voltage. We can also find the reflection coefficient in terms of dB, so the return loss from the horizontal scale, and everything is relative depending on the size of the Smith chart. So everything is like sort of like calibrated. So those scales are relative. So what really matters is moving from one point to the other. The starting point is not an issue. Starting point is the load, and you can calculate the angle of 2 beta L and you move certain number of degrees, or you calculate, or you know the L, how much it is in terms of lambda, the electrical length, and you move with this electrical length towards the generator or away, like towards the generator, which is away from the load, or away from the generator towards the load. Every time you move for a lambda by 2, you are back to the same point, because impedance and reflection coefficient, both of them are periodical quantities, and the period is lambda divided by 2. So based on that, what you really need is just protector, and so all what you really need is a protractor for like drawing a circle of constant radius, a calculator, maybe like an eraser, and like a pencil. You don't need to like a compass to measure the angle, because the angles is drawn. You don't need like something to measure the length, because the length is relative. You must use the scales at the bottom, and for the compass you need to just use the like radial scale on the circle of the Smith. So as I said, no need for like a ruler, no need for a protractor, just a compass and calculator, eraser, and pencil would be enough. So let us have an example to like practice what we have learned, which is trying to solve the problem using a Smith chart. So let us consider this case of a load impedance 40 plus J 70 ohm terminates 100 ohm transmission line, and the length of this circuit is 0.3 lambda, and we need to use a Smith chart to find the reflection coefficient at the load, the reflection coefficient at the input impedance, the standing wave ratio, and the return loss. So we need to solve this problem using a Smith chart, and then we confirm our graphical solution analytically. So we're going to solve the same problem twice. One time using the graphical method, second time using the analytical solutions that we learned last lecture. So as I always advise, so try to solve this problem yourself before you like continue with the video. So I suggest that you pause the video at this moment and try to solve the problem yourself. Once you completed your trial, successful or not, were able to complete it or not, you can come back and continue the video. This is my advice. Okay, so how would we start? So we start by normalizing our like load impedance. So the load impedance normalized to the characteristic impedance equal 0.4 plus J 0.7. Then we need to place this impedance on a Smith chart. So we'll find where is the intersection between the circle of 0.4, which is this one here. So we have the circle of 1, circle of like 0.9, 0.8, so on and so forth, till we find the circle for 0.4, which is this circle here. So this is the circle for 0.4. And then we search for so this is the real part, 0.4, which is here, this circle here, and its intersection with reactive part, positive 0.7. Positive is the upper side, so we search for 0.7 and we'll find it here. So we'll go the intersection between 0.7, this curve here, and 0.4, this circle here, is this point, and this is the Z small l, the normalized load impedance. Then we use our compass to draw a circle of constant radius that is passing through this point. So this is the load impedance, and this is the circle for constant reflection coefficient. From this circle here we can find reflection coefficient, which is the radius of this circle. Again, the radius must be read from the scale like this one here. So we go for the radius and we read the scale for standing wave ratio. We'll find the value from this scale. This is the standing wave ratio. The reflection coefficient is on this scale. So whatever we read, it goes from 0. Okay, so the reflection coefficient, this is 0. Depending on where is this vertical line goes, we'll find the reflection coefficient. The same vertical line here defines the reflection coefficient and the standing wave ratio. If the reflection coefficient is needed to be in dB, it also can be read from this scale. So we don't measure the absolute value because it's meaningless. It must be normalized to the size of the Smith chart. And for this, we just go vertically from this point here to find the reflection coefficient and find the standing wave ratio. And this is, we read the reflection coefficient, we find it's 0.59. We know the angle is measured from here to this point. The 0 is the right hand of the horizontal axis, so we can measure the angle from, we don't need a protractor, we can read the angle from the scale here. We see the 0, we read here, you'll find 104. So we know the reflection coefficient as a magnitude from the horizontal scale and angle from the circular scale. So from this point, we need to know the input impedance. We know the length, so we need to move from load towards the generator. Find that towards generator, so we'll move clockwise. You don't need to memorize. It's written on the chart. So we go from this angle, from this point towards the generator, and we move by 0.3. So we read the scale here in terms of lambda and add to it 0.3. So this is the point, and this value here would be Zn. So this is the input impedance, and this is also, we can use it as the reflection coefficient at the input. The reflection coefficient at the input does have the same magnitude as the reflection coefficient, but the angle now, instead of like 104, we just read the value here and we'll find it is minus 112. So this is positive, this is negative. You can use whatever scale, like from 0 to 360, or from minus 180 to plus 180. Both of them, of course, are correct. So we now solved input impedance and reflection coefficient for like standing wave ratio. So we can calculate the input impedance. Now this is a normalized value. We multiply by 100, we'll get the like absolute value. We can read the standing wave ratio from the scale. We can read also from the bottom scale the the return loss in terms of dB. So we have the reflection coefficient, the return loss, the standing wave ratio. All of them can be read from here. Standing wave ratio, we just have a vertical line from the intersection of the constant reflection coefficient circle with the horizontal line, and we go on this for standing wave ratio, for return loss, for reflection coefficient. Okay, so this completes the solution in terms of like graphical expression or like graphical tools, a Smith chart. Now we need to do this like analytically, and we'll confirm this. So you can do this analytically yourself. You'll find that this is the same or very close results. Of course, the analytical is more accurate, but the Smith chart is useful to visualize and like build your own intuition about what's going on the transmission line. One other interesting property of the Smith chart is that the Smith chart, so far we used it to like link between the reflection coefficient and the normalized impedance. Also, like the interesting feature of Smith chart is that we can use the same concept to relate the reflection coefficient to the normalized admittance. So if we moved by lambda by 4 away from ZL, the input impedance would be like having this value here. If we normalize this, it will equal the normalized, so this is a small letter, Z input, the normalized input impedance, lambda by 4 away from the load is Z naught over ZL, which is, if we just like express this value in terms of admittance, it will be YL divided by Y naught, which is the normalized admittance. So if we moved like lambda by 4 away from the load, what we are expressing is actually the normalized admittance of like our circle, and lambda by 4 is corresponding to 180 degree. So if we have any point here, if this is ZL, of course normalized ZL, and we moved like 180, which is like on the circle of constant reflection coefficient, we just go across the diameter. The other point would be the normalized admittance. So you can think of the Smith chart as representing like relationship between normalized impedance and reflection coefficient. The same chart can be also thought of as representing a relationship between the normalized admittance and reflection coefficient. To move from admittance to impedance, or from impedance to admittance, all you need to do is just move across the diameter on the same reflection coefficient, on the same circle. So this length must equal this length, and this way whatever you read would be the normalized, from normalized impedance to normalized admittance, or from normalized admittance to normalized impedance. There is some charts that combines both. So the red here, the red lines here, is the same Smith chart that we explained for ZL. On the same graph, they draw another like circles for admittance, which goes from here, and the circles would be like those blue curves are the admittance, the red curves are the impedance. On the same circle, on the same chart, we can consider the red circles to be admittance and the blue circles or blue curves to be impedance. Both of them are correct. So this is like the chart. Some people using this chart here, which I think is complicated. What I prefer is to use just one chart and know that we can switch the meaning of points like based on our understanding. So if I have, for example, I have a point here. Let me change this. So if I have a point here, so if I read from the red, it would be the this is 2, and this is, let us say, this is 0.8. Sorry, let me read this better. So yeah, so this is 2 plus j 0.8. This point here, let me return back. So this point here represents a value of 2 plus j 0.8. So if this is the normalized impedance, we can go across a line and draw okay. So we can go here and say, okay, this is the corresponding normalized admittance. So like, sorry for, it's not a straight line, but anyway, I hope you like following me. So I don't need, if we read here on the blue curves, we'll read the value of input admittance. If we do this, we'll read the value of input admittance. In order to have like a clean drawing, I would go with just one Smith chart, and this is the method that we're gonna use in our course this year. You will learn more from the next example. Okay, so we have a load of Z equal 100 plus J 50 that terminates a 50 ohm transmission line, and this line length is 0.15 lambda. Use Smith chart to find the load admittance, input admittance, and verify your answer analytically. So as I also like advised you early, try to like solve it yourself first, then continue with this video. Okay, so now this is like, this example is solved in the book with the two like the ZY Smith chart, but anyway, let us see how it's solved. So we calculate the normalized load impedance, which is 2 plus 1. So if we go on the circle of 2, it would be this circle. 1 is this curve, so we'll find ZL on impedance scale. So this is ZL. If we want to calculate input admittance, we have two ways. If we are using one chart, we'll go draw this circle here. This is the circle of constant reflection coefficient. So this is ZL on impedance scale. If we want to find YL on the same impedance scale, we go here. This point would be YL, the admittance we read on the impedance scale. We find YL. Okay? If we want to find like the Z input, if we want to find Z input, all what we need to do is to move towards generator. From ZL, we move towards the generator by the length. The length is 0.15 lambda. So this would be the Z input point. If we want to find Y input, either we read this point on the admittance scale or we go here to find the point on the impedance scale. I prefer to use one scale and just use the 180 relationship to move from admittance to impedance, to avoid having all of those lines, which is really confusing. So if we just do this, this would be ZL on the impedance scale. This would be YL on impedance scale. We move from here towards generator 4.15. This will be the point Y on the admittance scale. It will be the point of Z input on the impedance scale. If we want to find Y input on the impedance scale, we'll go for this point here. So this is Z input on impedance scale. We move 180 degree would be Y input on the impedance scale. And if we use just this one, we don't need to use the admittance scale, and you can verify the values using analytical solutions. So this concept that we just we're talking here about load impedance and input impedance, reflection coefficient, and standing wave ratio on a Smith chart was really practically can be used to measure the unknown impedance for microwave or RF, and what is used for this is slotted impedance. Slotted line. So the slotted line, you can consider here as you can put here some sort of a rectangular waveguide that does have a slot. When we study the waveguide part of this course, we'll know that this will not affect the wave inside the waveguide much. And you put the source from one side. So this is a generator, for example, and you put the unknown load here, and you use this device to find or to measure the unknown impedance. So how is that? So the idea here is something very similar to Smith's chart, as we're going to see. The main idea is that the reflection coefficient on the line is constant amplitude, and the second property or feature for this slotted line is that the input impedance is periodic with a period of lambda over 2. So let us see how this slotted line can be used to measure unknown impedance. So the standing wave ratio is constant, reflection coefficient is constant. The voltage on the line does have this expression, so it has a value multiplied by 1 plus this expression. We had reached this expression before in previous lecture in the analytical solution. So this expression for the measured voltage does have a minimum value when this property equal pi, and a peak value when this angle equals 0. So we can use this property to find the distance between the load and the first minimum. This distance equal we know the distance from the slotted line, we know the angle, we know the lambda, so we can find this relation here. This is known from the frequency, and this is measured. We know the minimum is happening at phi equal pi. So if we can measure this, we know beta from the for the frequencies that we used. The minimum would help us to find theta, and the ratio between maximum and minimum would help us to find standing wave ratio. From standing wave ratio we can measure gamma. So actually this slotted line can be used to do two things. the ratio between V maximum and V minimum. So we move on the line, we move like the measurement point on the line to find maximum voltage. We move again to find the minimum voltage. The ratio is standing wave ratio. This ratio can give us the magnitude of the reflection coefficient. We move away from the load to find the first minimum. The first minimum is corresponding to L minimum. We substitute it in this equation. We find theta. So this way, we measured Vmax, Vmin, Lmin. From Vmax and Vmin, we can find the magnitude of gamma. From Lmin, we can find the magnitude of theta. So we have gamma as a complex number. We can know from Smith chart or by calculation, we can find Z load. So let us apply this concept on this example here. So we have like two steps procedure to find out unknown impedance using a 50 ohm coaxial slotted transmission line. So a short circuit is placed at the load plane. So at the point of the load, we put a known load, which is a short circuit. This short circuit, of course, will result in a standing wave on the line. The standing wave ratio would be infinity because the maximum is a value, the minimum is 0. And we find the minimum as shown in the figure. So this scale can be placed anywhere, but we know that if this is a minimum, this is another minimum. So this is the place of the load. We have this scale. The scale can be in that way or that way. It can start here or start any point, because really what we are behind is the relative value between points. So when we have a short circuit, we'll have sort of like sharp minimum. The distance between minimums is the lambda by 2, because we know that the impedance is periodic with a lambda by 2 period. So we can use the short circuit to find the frequency. Then we put the unknown load and we find the position for the minimum. The minimum here would be much sharper than here. In general, the minimum is more steep than the maximum. That's why we are using the minimum to find out the unknown impedance. Of course, if we have like very sensitive measurements, we can use the peaks as well. We know the peaks and minimum, the angle between them is like lambda by 4. If you remember on Smith chart, the difference between maximum impedance and minimum impedance, maximum voltage and minimum voltage are 100 by 80 degrees, which is corresponding to lambda by 4. So, okay, when we have a short circuit, we find the minimum at 0.2 centimeter, 2.2 and 4.2. So the separation from one minimum to the other is lambda by 2. So lambda by 2 equal 2 centimeters. Then we remove the short circuit and we placed the unknown load and we measured the standing wave ratio, maximum to minimum. We found it to be 1.5. The voltage minimum is recorded at those values. Okay. So this is at first one at 0.2 in this case, and here at 0.72. So because it's periodic and we know this is corresponding to like short circuit, so we can assume this is the place of the load. So the distance from this point, the minimum in this case, to the first minimum in that case is L minimum, which is here 0.72 minus 0.2. So L minimum is 0.52. And this way we would solve the problem. So lambda by 2 equal 2. So lambda equal 4. Okay. Okay, sorry, so the load is here, so we need to find the distance from this minimum to this minimum. Okay, so if this is the first minimum from the load side, so this is the position of the load, and this is 2.72, this is 4.2. This distance here is the distance between the first minimum and the load. Sorry, we're assuming the 0 is 2. So we go from the first minimum closest to the load, and then we measure the difference to the first minimum in case of unknown, which will be this distance. So this distance is 1.48 centimeter, which is corresponding to 0.37 lambda. We just calculate reflection coefficient. We substitute L minimum into this equation to find theta. So we have the reflection coefficient with 0.2 magnitude, 86.4 angle, which gives us the reflection coefficient in real and imaginary format. This way we can use the relationship between gamma and Z to find the load impedance, which will come up to this value here. We can solve the same problem using Smith's chart. The load is, the load is 0.37 lambda away from the first minimum. We know that the minimum on Smith's chart is on the left horizontal axis. We know that the standing wave ratio is 1.5. So we can go on Smith's chart on the scale at the bottom and measure or locate the position for 1.5 standing wave ratio. Then we go vertically with a line. The intersection of this line with the horizontal axis would be here. Then we draw the circle of constant standing wave ratio or constant reflection coefficient. This would be our points. We know that this is the position of the load, and then we measure the distance. We move from load towards generator for 0.37 lambda. So this is the location for the first minimum. In order to find the load impedance, we go from this minimum towards the load by a distance of 0.37 lambda. So this is the location of the first minimum away from the load. If we move towards the load by 0.37 lambda, we'll find the load impedance. So like Smith's chart is helping us visualizing the problem and make the solution for me a bit easier than the analytical one. One other topic to cover is what is called quarter wavelength transmission line. So it is a special case when we have a transmission line of lambda by 4 length. So let us consider this circuit. We have two transmission lines, transmission line 0, transmission line 1. Transmission line 1 does have the length of lambda by 4 and terminated by an impedance RL. So what this is about what's called impedance transformation. So it's one of the methods to have impedance matching. Impedance matching means that for Z0 we want to have zero reflection coefficient. So Z0 is loaded by a section of Z1 that is loaded by RL. the load that we see on Z0 is the load that we see here, the impedance we see here, which is the input impedance to transmission line 1. So the input impedance for transmission line 1 is the load impedance RL moved like lambda by 4 towards generator. So Z input equals Z1 multiplied by this expression, and if we just do the math for lambda by 4 length, we'll find that equal Z1 squared divided by RL, the load impedance. So the input impedance here equals this expression. If we can choose Z1 such that this expression equals Z0, we will have no reflection coefficient here. So if we choose Z1 such that Z1 squared over RL equals Z0, we will have 0 reflection coefficient here, and we did like generate some matching network for Z0. So this is called sometimes lambda by 4 matching transmission line, or lambda by 4 impedance transformation. Why? Because for lambda by 4, if this is real, the input impedance would be real, and we can use the choice of Z1 to achieve matching. So this is a very common practice in microwave engineering. So let us apply this on the following example. We consider a resistance of 100 ohm that need to be matched to a 50 ohm line using a lambda by 4 transformer. Find the characteristic impedance of the lambda by 4 matching. Plot the magnitude of the reflection coefficient versus the normalized frequency f over f naught. Okay, so the idea here is that lambda by 4 will equal lambda by 4 at a single frequency. When we change the frequency, lambda will change, and the physical length of the transmission line is constant, so it will not be lambda by 4 anymore. So lambda by 4 transformer is working at a specific frequency, which is corresponding to the length of lambda by 4. For change of frequency, lambda will change, and this is same physical length will be corresponding to a different portion of wavelength. So we just do the math. We need Z input here to equal 50, which makes Z1 equal the square root of 5,000, which is 70.1. So if we have a 70.1 transmission line segment that does have the length of lambda by 4, and we have a load of 100 ohm, this load is matched to the 50 ohm transmission line because of this impedance transformation. So L equal lambda naught by 4 at this specific wavelength. L equal lambda by 4, and if we want to do the math for calculating the input impedance at different frequency, we can just follow the math here. The speed of light equal lambda f also equal lambda naught f naught. So for any frequency, if we increase the frequency, lambda will decrease. If we decrease the frequency, lambda will increase. So the reflection coefficient equal ZL minus Z naught. So we can find the reflection coefficient, and we find the reflection coefficient for here. Z input would have this expression at different value other than f naught and lambda naught. Beta L will not be lambda by 4, so L will not be lambda by 4, so this will not be 90, and just substituting into this equation and plotting it on MATLAB or so, we'll get something like that. for f equal f naught, we'll have a perfect matching. Whenever we move away from f naught, we'll have some reflection. But if we move to 3 f naught, so the length would be like 3 over 4 lambda. So at this frequency is higher, so the wavelength is smaller. So the same length here, which equal lambda by 4, here will equal 3 lambda by 4. So 3 lambda by 4 and lambda by 4 does have the same effect because they are lambda by 2 away from one another. So the input impedance at lambda by 4 and at 3 lambda by 4 is the same value. The input impedance for this section here would be equal Z naught. The input impedance here equals Z naught when this is lambda by 4. Also, it will equal Z naught when this is 3 lambda by 4, when this is 5 lambda by 4, when this is lambda by 4 plus any integer number of lambda by 2. And this is what we're seeing here. So this is like an example to explain the use of lambda by 4 impedance transformation. So far, all what we are studying is sort of like the steady state analysis of microwave circuits. There is another aspect, which is the transient analysis of transmission line circuit. So the idea here, the main idea here is that the wave, the electromagnetic waves, doesn't see the future. So if the wave is propagating at any point, it just see what is happening at this point. It doesn't see the future. It doesn't know how far it is from the load. The wave is propagating till it reaches the load. When it reaches the load or any other discontinuity, it will start to respond. So the idea here, the same problems that we were discussing here. We have section 0 transmission line, section 1 transmission line. For the length here can be whatever, and there is a load RL. So what we covered so far is the steady state analysis of that problem. What about the transient? So what is happening over time? And this is very fast because we are in the microwave range. So if we are transmitting a signal here from this point, the signal will propagate. The signal at any point, just here on this line, it's C impedance equals Z naught. No change, so the signal will continue. The first change that the signal would see is at this point. What does the signal see? It just see Z1. It doesn't see Z input. We are transient. The signal just see immediately what is happening at this point. So when the signal reach here, we have Z naught. Then we see like input, the impedance of this section is Z1. So the signal see Z1 here, and the wave is propagating on Z naught. So there will be some reflection here. Let us call this reflection gamma 1. Then gamma 1, part of the signal will be reflected and part of the signal will be transmitted. This is transmission 1. Transmission coefficient 1. The signal travel, no change here. The T1 portion is moving. It just sees Z1, no change till it reaches to this point. When it reaches this point, it sees RL different than Z1. So there will be reflection coefficient 3. Part of the signal will be delivered to the load and part will be reflected. The reflected signal is moving on Z1, no change, no change. The first change it will see is this point. At this point, it will see a load of Z0. So there will be reflection, gamma 2, and transmission T2. This will happen because the reflection coefficient is always less than 1 when we move round trip. Every time the signal is getting smaller and smaller, so we have a conversion for our solution. So we can use this transient analysis method to calculate the total reflection. So what is the total reflection? So the first wave, when it reaches at this point, it reflects gamma 1 and it transmits T1. T1 will travel till it reach here, so it will reflect gamma 3. So the signal here now is T1 multiplied by T3. It come here, part of it will be transmitted here, which is T2 multiplied by T1 multiplied by gamma 3. Part of it will be reflected, which is T1 gamma 3 gamma 2. So here, this is another way to draw it. The signal is 1. We have like reflection coefficient gamma 1, transmission coefficient T1. The transmission coefficient will go here. We'll have gamma 3. When it reach here, we have T2. So what we have? T1, gamma 3, T2. And it is traveling here. The signal travels here lambda by 2. So it has a negative sign because it travels lambda by 2, which is corresponding to pi, which is corresponding to minus 1. Then part of it will be reflected, gamma 2, gamma 3, T2 again, but again another lambda by 2, so minus 1, minus 1. So we'll keep having this sort of like geometric series. Each time it is getting smaller and smaller. And what is the like geometric coefficient? It is gamma 2, gamma 3. So this one, starting from this element here, we have, this is the first element of the geometric series. Second element is first element multiplied by minus gamma 3, gamma 2, so on and so forth. This way we can find the summation, we can find the solution, and like the infinite series here of geometric like series is converging. We can calculate gamma 1, gamma 2, gamma 3, transmission 1, transmission 2, and do the math. We'll find out the total reflection coefficient, the total signal that we see here after a large number, like 5-6 times of getting back and forth, will be converging to the reflection coefficient that we calculated for the steady state. And like the good point here, that or the important point that we need to learn here is how to think about the transient analysis and how the microwave signal just see what is happening immediately. It doesn't see the future. If we are thinking about transient analysis, we need to follow this intuition here. As I said, we need to just like, this is the coefficient. Here we can find the value by the summation for infinite number to steady state or any large number, because after a while this will be like a reflection coefficient less than 1 multiplied by reflection coefficient less than 1, and this is happening for long time, for large number of reflections. This value would be like getting smaller, and the reflection coefficient like the summation will equal this value. So the total reflection coefficient would be gamma 1 minus the sum of the geometric series. If we take this element here, then we sum for a large number, we will find the expression for the steady state reflection coefficient, but this time we are coming from the transient analysis angle. There will be a homework number 2, which is due in a week from our discussion session, and these are the points that we discussed and learned into in this lecture. Hope that is useful, and hope that you like do effort to understand the concept and the logic and math behind the Smith chart. because it simplifies the solution of many microwave and RF problems. Thank you, and meet you in the discussion session.